So let's take this example. You're in an online call and you want to blur out the background. The computer has to know where the subject is in the frame and cut them out, all just from a two-dimensional image. Now, your human eye can do this in an instant, but the computer might need a little bit of help. So in the last video, I actually talked about how the human eye is able to instantly detect an edge.
Answer my question. Were you edging or were you gooning? Answer! Gooning.
And now I want to talk about one of the earliest applications of computer vision models, and it was actually designed back in the 60s and 70s. And it was for edge detection, which is very important for detecting edges of a subject in a photo, or detecting different contours and different lines throughout the image. It's mainly comprised of 3 steps. The first one is grayscaling the image. The second one is applying the Sobel filters. There's 2 of them, and we'll talk about those. And then the third step is to find the magnitude between those 2 filters, and that'll give you your subject in the image. So diving a little bit more into the actual technique that is used, the first step is to apply the image to become a grayscale image or an intensity image. That means we're taking away all the color, and every single pixel is now just going to be a brightness value from 0 to 255. So 0 would be completely black, or 255 would be completely white, or sometimes it can even be 0 to 1. It just depends what you're working with. So after turning it to grayscale, we want to detect where the edges are in the image. We can do this by measuring the gradients on the differences of the intensities between the brightness of the pixels. So imagine it like a bunch of hills and valleys, and we are measuring the steepest of the gradients from the top part of the hill down to the bottom. So the top part being completely white to the bottom part being completely black. And we're measuring the brightness of each pixel in relation to the pixel next to it. And this is just a simple rise over run that you learned from the early calculus days. So let's take a look at an easy example. In this image, you can see where all the zeros and ones are, and you can definitely tell where the edge is in the image. But it may not be as simple when you have an image that looks like this. The Sobel operator works by detecting the gradient of intensity. This gradient is read with a vector that has both magnitude and direction. So the direction can be read by taking the x and y components and taking the inverse tangent of them, while the magnitude is taken by looking at the gradients along the x and y components. What you're left with is a bunch of arrows that kind of look like the hills and valleys that point from the brightest points to the darkest points. These are the gradients of intensities that we're talking about. The next step is to actually approximate the gradient using a 2D filter or mask that will be convoluted over the image. Now, convolution is a big word, so stay with me now. But convolution works by sliding a small window or a kernel, and it performs element-wise multiplication on each of the corresponding pixels. Think of this as a magnifying glass that scans over the entire image and calculates the output on the destination layer. So in this example, you'll see that the -1 is multiplied by 5, plus 0 multiplied by 2, and so on until you get the final value of 5. The Sobel operator uses 2 different masks to detect the edges in both the horizontal and vertical direction. And then we take the horizontal and vertical edges, and then we find the magnitude between them to find the final output image. So to wrap things up, the Sobel operator was one of the first successful computer vision models that was able to detect edges in an image. And this has really impacted how we use our technology today, from things as facial recognition, self-driving cars, and even home security systems. And in the next couple of videos, I'll be talking more about these other operators, along with the different methods and techniques that are used to help improve their efficiency. I should also mention that in practice, all of this works perfectly, but in reality, there's always a lot of noise and extra edges that are detected that we don't want. And so we have to do a lot of noise filtering and thresholding techniques to make sure that these edges are the ones that we want. So I'll be talking more about that in a future video.